Thank you. First of all, thank you for showing up for the closing keynote. I know it's been a long day. My name is Gabor Szarnyas, and I'm here to talk about the evolution of data management techniques. But first, a few words about my personal evolution as far as my career goes. I studied computer science and I did a master's in query processing, namely graph query processing. And I found that this problem is so hard that I started a PhD of solving the same problem, but in a distributed setup. So that yielded a nice PhD thesis, and then I moved to Amsterdam to work at CWI. Do you know what was invented at CWI? Python, indeed. Python. Guido van Rossum invented Python at CWI. So I worked there in the database group. And as I was working there, something else was invented. This was DuckDB, a database system. And the co-creators of DuckDB, Mark Rasfeld and Hannes Mühleisen, created a spin-off company called DuckDB Labs, which is the company I joined a couple of years ago. So what is DuckDB? For a superficial overview, DuckDB is an open source analytical database as a library. Think of it as a database in your pocket. If you have a Python script, you can just say import DuckDB, and then you can start firing SQL queries right away. You can do aggregations, filtering, projections, and all the usual SQL stuff. But this talk is not a DuckDB product talk. This talk is about a few trends in data management, like the prevalence of columnar storage, binary formats like Parquet and Data Lake. And what I try to shine a light on is why the field evolved, how it evolved, and yes, sometimes I will talk about DuckDB because I will try to explain how certain changes are captured by the DuckDB software. But I will also say plenty of nice things about our competitors. So let's get started with big data. Who has heard about big data? Most of you have. This was all the rage in 2010 when I did my master's. People said that there are three V's. There is the variety of data, the velocity of data, and the volume of the data, with the last V, the volume, being probably the biggest problem. And looking back, it's sometimes a bit weird why people build these 32 or 64 node Hadoop clusters. So I thought I will bring you a little story to illustrate the problem that people faced 15 years ago. So let's imagine the year is 2010 and we are fresh off of a financial crisis, which is a bit scary to say now. But in any ways, the crisis happened back then. Housing prices plummeted, so you could actually afford an apartment. So you bought an apartment and you want to throw a nice housewarming party. And because the year is 2020, you post your invitation on Facebook and you ask your friends to come by and maybe bring a +1. But when you open Facebook the next day, you found that 50 people signed up to your housewarming party. And that's the problem, because even though they may be able to fit just, cooking for 50 people is difficult. The previous owner left you this very basic kitchen with just 2 cooking plates on the stove. It's not hard to see that if you want to cook and you want to cook 50 meals, you're probably going to be ready by 4 a.m. most of the time. By that time, your guests will be gone, hungry and grumpy. So what can you do? Well, you can order online. You can call a restaurant, and the restaurant has pretty good cooking equipment. They have these super powerful industrial ovens with many burners on top, and they actually have many of these, so they can scale. For restaurants, it's not a problem to make 50 meals in a matter of an hour. Meanwhile, in the computing world, something very similar happened. People were sitting in front of their laptops and were wondering whether they can solve their data problems. The problem is that little basic kitchen is quite a good analogy for a laptop in 2010. Laptops in 2010 had maybe 1 CPU core or 2 CPU cores. They had a hard drive with rotating disks and limited amount of memory. So with that, even if you only have like 100 gigabytes of CSV files, that counts as a big data problem. So what did people and organizations do? Well, they outsourced the problem online. They went to one of the cloud providers, they rented out the cloud machines, and then they rented out the software that runs on them. And over the coming 10 years, a pretty impressive stack was built. We have systems like Amazon Redshift, Google BigQuery, and Snowflake. And these take care of most of your big data problems. They also take care of your savings, because these are rather expensive. You have outsourced the problem, but you will pay handsomely for it. And there are other complexities involved. For example, you have to shift the data back and forth sometimes, which is expensive because of the egress costs and takes some time. Still, this does solve the big data problem. And over the next 15 years, the only major change was that this kept getting more and more expensive. These days, it's not unheard of to hear companies saying they spend millions of euros on their cloud bill every year. So I would argue that this is pretty much equivalent to getting to a point in your life where you order food online every single day. It's sure convenient, but it's definitely not efficient, it's very expensive, and actually not that healthy. So what changed in the last 15 years? Quite a few things. The first being the hardware. If this was a good analogy for a laptop in 2010, today's laptops are more like this futuristic spaceship-style kitchen with 10 induction cooking plates. With this, you can probably cook for 50 people. These modern laptops have 8, 12, or 16 CPU cores, they have NVMe SSD disks, they have pretty large amounts of memory, 16 gigabytes of more, so they can actually do some heavy lifting, especially if the software is up to the task. Because the other thing that changed is the storage and execution layer of the database systems. For this, I brought you a little table inspired by the Raven network of Lithuania. The table has 3 columns: the date, the station, and the delay that a particular train has faced. I hid a bunch of extra columns. Obviously, there is more to this. So how would you store such a table? If you open an old database textbook, they would say that you store the data by row. That means that logically, you will treat the data set on a per row basis, and then physically, you will also store elements in a given row together. This is very simple conceptually. You can always add another row, you can delete a row, you can update a value. But if you want to do some computation on it, it's not nice because it will be full of random accesses. Another approach is to use something called column-based storage. Here, the unit that you treat is a column, so entities in the same column are in the same physical space on the disk. And this yields a bunch of benefits. For example, you can see that similarly typed and similar valued entities are close together on disk. So you can say, well, all of those dates are the 21st of April. Let's just compress it. And same for the delay. We can do some run length encoding on the delay. And if we compact it, then we basically saved half of the data size. So we have row-based storage and column-based storage, and they come with their own individual trade-offs. They also come with their own individual execution models. If you store the data by row, what most systems do is the row at a time execution model, which is an iterative model. You go row by row, and every row is read from beginning to end. Then you process it, then you adjust the average delay that you have calculated so far, and so on. So if you want to compute the average delay per day, you will do something like this. Now this is conceptually simple, but rather inefficient. It's not really in line how modern CPUs work, and it reads more data than necessary. So maybe this should be flipped too. We should do something called column at a time execution. This has an immediate benefit. If we ask what is the average delay per day, we can just drop the station because that is not important for the analysis. And then we can take the 2 columns, give it to some CPU thread, and that will do some magic and just go through the data with long sequential scans. This is nicer, but the problem is that the column is treated as a whole. And if you have a column of 10 billion entities, you are bound to run out of memory. Pandas is an engine that does column at a time execution, and you may have seen out-of-memory errors with Pandas. This is just something that doesn't scale with the data. So somewhat of an in-between approach is called vectorized execution. In vectorized execution, we have vectors, that is chunks of data, that are processed together. For example, here I picked a vector size of 2, so we have 4 vectors for each column. Then we distribute these among the CPU threads, and then we do the processing in a way that the data that we are processing typically fits into the L1 cache of the CPU. Obviously, there's quite a bit more going on. We are building hash tables, we are merging together the data sets, but the conceptual idea is that we are using these vectors, and this yields something called vectorized code, which means that the CPU is using SIMD or SIMD instructions, single instruction multiple data instructions, which are more efficient than item by item, like iterative processing. And this is parallelism friendly, it's easy to distribute, and it's cache friendly because you can make sure that most of the computation fits into the CPU cache. So this was the storage and execution part. And the third part of the big changes is the realization that indexing has a different role in analytical workloads. If you have studied computer science as an undergraduate, you probably learned about B trees or B plus trees, and you learned that you should build these trees on the high selectivity queries that target a given entity, and that will allow you to find them faster. This is true, but in analytics, we rarely do those sort of operations. In analytics, we mostly do scans, aggregations, and maybe simple filtering. So in analytics, B trees can actually slow down your workload or not be used at all. And what works better is something called min-max indexes or zone maps by other systems, which is a really conceptually simple idea. I added some more data here and turned it into 2 row groups. And what the min-max indexes do is that for each row group, they define the minimum and the maximum value for each of the columns. So you have this high-level aggregate statistical data in your metadata. So you can see the minimum date, the minimum station, the minimum delay, and the maximum for all of these columns as well, both in row groups 1 and row groups 2. And this is great because if you have a question like which stations were affected by delays larger than 2 minutes, then you can just read that part of the statistics. You can identify that if the maximum is 1.6, there will not be any larger than 2, so you can dismiss that immediately. Thanks to the columnar storage, you can dismiss the date because no one really asked about the date. And then you can do the filtering, yielding just 4 cells of your tables. So you basically could go on about evaluating your query without touching 2/3 of your data, which is a huge win. So what I have lined out here, columnar storage, vectorized query execution, out-of-core execution for larger than memory processing, and the SQL language is something that has kind of solidified in the last decade. And this means that most systems now, at least for analytics, use an architecture like this. This is what Snowflake does, this is what Databricks and ClickHouse do, and this is also what DuckDB does. And the underpinning of this, the columnar storage and the lightweight compression and lightweight indexing methods, they are part of these systems, but they are also part of popular formats like the Apache Arrow format for in-memory data exchange and the Parquet format for storing data on disks. And this actually pushed performance to quite a large and great extent. Are you familiar with the TPCH benchmark in the database world? I see some nods. This is the benchmark that is the gold standard in analytical data processing. In the early 2000s and in the 2010s, vendors fought fierce battles on winning this benchmark. And by vendors, I mean Microsoft, Oracle, and other database vendors, as well as Lenovo, Dell, and other hardware vendors, because this was a coveted prize that vendors were fighting about. So the TPC did these intricate audits for systems, and they labeled systems with a TPC price, which is in the range of $500,000 to $1 million usually. This is the ownership cost of the system and the TPC throughput and scale factor that a given system can do. But a couple of years have passed, and the TPC benchmark, even if not trivial, became rather easy. The 1000 scale factor version, which is 1 terabyte of CSV file, is now something that DuckDB can run on a Raspberry Pi with 16 gigabytes of memory. The 10 terabyte one can be run on a top-of-the-line MacBook Pro, although a little footprint is that you cannot store 10 terabytes of CSV on the MacBook. You have to store it in the database format. And just last week, I completed an experiment where I spun up a big AWS instance with 1.5 terabytes of memory. And this completed all TPCH queries on the 100 terabyte workload. This is, of course, rather impressive. Like 10, 15 years ago, this was not possible unless you had a distributed cluster of computers, which was very expensive to set up and run. But this is not really about how great DuckDB is. This is about how great this vectorized execution model and columnar storage is. Because there is nothing secret about this. There are papers on how to implement this. DuckDB is open source. So the competition is already in a similar vicinity of us. And if they are not, they can copy many of the improvements and optimizations that we made. And I think this is important because this means that performance is no longer the deciding factor when it comes to picking a database system. What is more important these days is the ergonomics. And starting about the ergonomics, the important is how you set up the system and what is your initial 5-minute experience with the system. So traditionally, systems did something called a client-server architecture. On the left, there is a client application sitting on a laptop or a terminal, and on the right, there is a big iron server. Why did people settle for this for decades? Well, because the laptop was rather weak and you couldn't really do big data processing on the laptop. You had to do it on the server. But this setup has a bunch of issues. First of all, the server is usually closely guarded by the sysadmins. So you cannot install stuff on it. You cannot just SSH into it. You have to open a ticket and you have to get your user. You have to configure your connection string. And then there is the matter that this is a rather thin straw. It is slow to serialize data on the client protocol. The network is not really fast. So it's kind of a clunky and not that efficient system. But still, this was the dominant approach for multiple decades, as exemplified by all these systems like MySQL and Postgres for transactional workloads, Snowflake, Databricks, and ClickHouse for analytical workloads. But we at DuckDB thought, how about flipping this architecture and putting the client application on top of the database and the database into the client application? In this case, there is no need for the server. You already paid for your laptop, so that's just sitting on your desk anyways. And you can put your data in a single file. Of course, realize that this is not something we invented as an architecture. SQLite has been doing this for transactional workloads for decades, and it has been widely successful in doing so. But DuckDB is the first system that does it in an analytical setting. Of course, this doesn't come easy. One of the big problems is portability, namely that unlike the client-server systems, which only have to ship a thin, simple client to the client applications, we have to ship the entire database system and make sure that it runs on x86, it runs on ARM, it runs on Apple Silicon when Apple decides to ditch Intel, and it has to run on mobile phones, handheld devices, servers, etc. And this actually requires quite a few compromises. So DuckDB is a code base that's written purely in C++11 without any external dependencies and any platform-specific code, which of course puts a big burden to the developers. We also need to package DuckDB, the entire database system, for every single client. So we have Python, R, Node.js, Java, and other clients, and we do this for a big build matrix that includes many of the platforms. But once we are done this, we have nice, neat packages. And because this is PyCon, I'm really happy to talk about some of the Python features that you can do in an in-process system. The first is that you can very easily integrate with other libraries. Because DuckDB runs in the same namespace as all the other Python libraries, the interaction is trivial. You can just say, I start with some SQL query in DuckDB, but then I want to do some machine learning on it, so I need a NumPy array. In that case, you just say .fetch NumPy. DuckDB will write that NumPy array for you. It will give you a pointer, and you can start doing NumPy operations like np.sum right away on that. Probably even more important is the pandas integration. We encounter many cases where people already have an intricate pandas ecosystem with lots of operations, but they have maybe one operation which is a bit small. Well, with that, you can just target that pandas data frame with DuckDB. You can just say mydf, and then DuckDB will say, hang on, I don't have any table called mydf. Let's do a replacement scan and look around in the scope. It will find the pandas data frame then, and then it will do it. It will just read it through a zero copy mechanism. And because DuckDB is parallel, vectorized, and has an efficient query engine, we actually read pandas faster than pandas itself. So you can speed up some of your pandas workloads with DuckDB. And finally, one thing that has been traditionally really difficult in database systems is defining user-defined functions. If you have an Oracle database running in your on-premises cluster, you will not be able to put some Python code to run on the Oracle database. But with DuckDB, because you're in the same namespace again, if you want to do something like fake name generation, you just import the faker library. You spend a few lines of code explaining to Python that you need a function in SQL that's called random name that calls the get random name Python function, and you can start generating fake data right away. Another important part of the user experience is, of course, the user interface. Databases haven't been really friendly towards users. Most databases have the out-of-box experience like Postgres, so you start it and then you get a terminal with a blinking cursor. DuckDB can do this really well, but we thought that maybe it would be nice to have a more friendly environment. So we have a notebook interface that can be launched from the DuckDB command line client, and this is SQL only. But we also integrate with Jupyter, and now we have a Marimo notebook again. And this is something that is, again, not exclusive to DuckDB. Databricks have invented their own notebook ecosystem. So did Snowflake, and ClickHouse is also now integrating with notebooks really well. It's a common sentiment among data scientists that they like data frame APIs, but they don't really like SQL. And honestly, I can see why. I took the data that I showed you in the storage and execution model section and turned it into a CSV file. So we have date, station, delay, and all the data encoded it. And we just want to answer something really simple. What are the average delays per train station? I wrote a Postgres script to answer this, and it looks like this. We start with a detailed elaboration that there is a table called trains, there is a field date, which is a date, there is a station, that's a varchar, and so on. Then we specify how to copy this from the file with painstaking detail to the file format, header, and delimiter, and then we do a SQL query. DuckDB makes this a lot more simpler. Our friendly SQL extensions make so that you can just read a CSV file, and DuckDB will do something called sniffing, which is similar to what Pandas does. It will go through the CSV file and it will try to figure out the delimiter and the types and the column names. And if your CSV file is reasonably well behaved, this works rather well. But we took this a bit further and we say, why do you have to create a table in the first place? Why not just run it directly on the CSV file? So you can put trains.csv directly into the from clause. And here comes my favorite bit. I was always bothered by how you always have to say select date, station, and the aggregate, and then group by date and station again. This is something that the computer could just figure out on its own, right? So DuckDB has this construct called group by all. And group by all is ensuring that it will do the aggregation on all the columns that are not listed in the aggregate function itself. And it seems that we really hit a nerve with this group by all, because DuckDB released this in 2022, and over the coming years, basically every single vendor copied it, and it's now available, at least in a preview state, in most of the analytical database systems. And there are a bunch of other nice innovations in the friendly SQL space. And yes, sometimes we borrow ideas from other vendors too. I think this is great. And if you picked up SQL maybe 10 years ago and didn't like it, I really encourage you to give it a try. It has become much nicer to use in the past few years. So I promised I'm going to say nice things about DuckDB's competitors, but who are those exactly? So we have this space, and I would exclude the transactional systems because they are not fit for analytics. And I would also exclude the analytical proprietary systems because of their very high pricing. So that leaves us with ClickHouse. And ClickHouse is actually released something called CHDB, which is the in-process version of ClickHouse. So they follow the form factor of DuckDB in that. And I would also add Polars, which is not traditionally a database system, but it's a state-of-the-art data frame API and query engine. So how do these systems stack up? I would say that these are all really well-engineered systems, and they all follow the best practices that we talked about. They are columnar, they use vectorized execution, they employ lightweight compression and lightweight indexing, and they have a reasonably new lean code base. And I think if you're using any of this, you're already kind of in good territory. And if you're not using this, I think it's usually pretty simple to make a choice. ClickHouse is best if you have really large data sets that probably benefits still from running on a distributed environment. They recently released a benchmark where they have 1 trillion rows, that's 10 on the power of 12 rows. If you have that size of data, then ClickHouse is great, especially if you need fast updates for it. ClickHouse is the only one from this bunch which works in a client-server setup, which is beneficial in a bunch of scenarios. And in that case, ClickHouse is great. If you don't need client-server ClickHouse, then you can, but you already have ClickHouse SQL snippets and you already have some foothold in the ClickHouse ecosystem, then go for CHDB. This is ClickHouse packaged in process and it runs in Python. Polars is mostly for people who want to migrate away from pandas. It's a data frame API, it has great arrow integration, and being written in Rust and primarily focusing on Python, it has the best Rust and Python integration. And DuckDB is probably the best choice if you need full SQL support, if you need ACID transactional guarantees on your updates, and overall DuckDB is the most lightweight, as in the fewest megabytes, and is the most portable system with the most clients available. So on to part 3. Part 3 is about data persistence and mutability. And this is a bit of a head scratcher because why would this even be a problem? Databases could update data already 50 years ago, so it's not like we need a significant innovation in this area. Well, it turns out that we do. Around 2005, a new sort of architecture started popping up. It was called disaggregated storage. What does this mean? It means that we have a compute layer of compute nodes, typically virtual machines, and a storage layer in some sort of an object storage. If you were on premises, it was Hadoop. If you were in the cloud, it was an S3 bucket or a similar object storage. And the compute layer in the cloud, of course, some sort of virtual machine layer as well, like AWS EC2 for elastic compute. And the idea here is that you should be able to scale your compute independently from the storage layer, which is a really nice idea. But the storage layer is a tricky one because these storage layers are implemented as distributed file systems, which are not that similar to local file systems. These provide you high availability, these provide replication at the cost of using immutable files. If you put a file there, then it's there. You cannot really update it. In most distributed file systems, you cannot really append to it either. You can maybe delete it or just add the new file next to it. And this is, of course, not ideal if you want to run a database with updates, so much so that an entire new architecture is needed to accommodate for this. And this new architecture was invented starting from 2010 when Google BigQuery was released and then later by Snowflake. And what these systems achieved was that they separated the compute layer and the storage layer in a way that you can scale them independently. And they invented storage formats in the object storage that allowed the database to still update the data. Of course, they had a proprietary format, so that was sitting on your own S3 bucket, but you couldn't really do anything with it. If you wanted to do anything with your database, you needed to write an extract job, transform the data into some format that can be consumed by your script. And if you wanted to do a machine learning job, you transferred the data there on an EC2 instance, you did that job, and then maybe you even had to write it back to the database. So this is all a bit clunky and definitely not a nice user experience. And one more thing, remember how this was also insanely expensive? Companies are not really happy about the fact that they have to pay these cloud vendors enormous amounts of money. So starting from around 2015, the data lake architecture was popularized. In this architecture, in the storage layer, instead of using a proprietary format, we use a data lake, which is built on open formats, and it allows all these entities in the compute layer, including the database, the machine learning job, but maybe also other query engines and data science jobs, to coexist and to work on the same data set. This is where it bodes into the multi-engine stack. You can have an architecture where you have multiple databases and multiple query engines and always use the right tool for the job. Now, of course, it cannot be just one piece of technology. These days, we have 3 data lake formats fighting for glory. One is Delta Lake, originally by Databricks. The second is Iceberg, originally by Netflix. And then Hoodie, which was invented by Uber. These are largely similar. So they all use Parquet files at the bottom for storage. And that is their data layer. And they build a metadata layer of JSON and Avro files on the top of that. And overall, they solve this very hard problem of providing transactional updates in an object storage in an open source manner. They also introduce neat features like time travel queries, because if you cannot realistically delete files, then it makes sense to ask queries what happened as of last Wednesday, what were the statistics of the sales back then. And then you can also do schema evolution, which is of course necessary. If your data is up for a long time, you will update your tables. However, if you go to any of these data lake meetups, you will hear people complain a lot. They will complain about performance issues. They will complain about something called the small files problem, where you have fragmentation in your files, and then you have these tiny Parquet files accompanied by a dozen metadata files. And they have all sorts of convoluted workarounds on compaction, which means you just try to rebalance your files and try to just reduce the number of snapshots sometimes just to get away with storing much data in a data lake. But interestingly enough, this seems to be the hot topic of 2025. Because the performance has converged and systems largely implement the same performance now, users care more about the ergonomics of their systems, and they care more about the file formats. And this was exemplified last summer when Databricks, who already invented Delta Lake, bought a company called Tabular, who employed most of the contributors for the Iceberg format, for the rumored price of $2 billion. So this is really the hot topic today, and this is something that has big implications. And as we speak, there is probably another catalog company coming up which tries to build an entire database on top of a data lake. How is this reflected in the Python world? Well, in the Python world, there is this really strong, almost exponential rise in the PyIceberg library. This is a very advanced Iceberg library that allows you to read and write Iceberg format. You will probably use it at some point if you're in a data engineering role. And how does DuckDB stack up in the cloud? I would say that we have a fairly broad and complete cloud offering with some immaturities here and there. Overall, the columnar storage and the related execution techniques work really well in the cloud. And let me give you an example for that. So let's say that we want to run the query again. Which stations were affected by delays of larger than 2 minutes? What DuckDB will do is that it will activate the HTTPS extension, the Parquet extension, and the AWS extension to evaluate this query that targets trains.parquet in an S3 bucket. But it will not do so in a naive way where it downloads the file and then decodes it and then runs the query. Instead, it will make use of the same min-max index metadata that's available in the Parquet file. So it will actually just read the metadata bit of Parquet using something called HTTP range requests. It will find these values. It will make the same decision as it would make locally, that we don't need row group 1. Then it will seek into row group 2 and get those two. And then it will do the processing and return the relevant columns. And again, we have saved 2/3 of the work, which is even more important because we are communicating with AWS over the wire with high egress fees. From the other technologies, we have Iceberg and Delta support, currently with read-only support, but both are under active development. We have been collaborating with AWS to support their S3 tables catalog for their Iceberg integrations. And reading the news, ClickHouse also announced that they are doubling down on Iceberg and putting a lot of engineering effort into making that work with ClickHouse. And a final word about MotherDuck. Tomáš already said in the introduction that DuckDB and MotherDuck are not the same piece of technology. And indeed, MotherDuck is a cloud data warehouse that's built on top of DuckDB. So you can think of it as Snowflake, but with DuckDB in its heart as the query engine. MotherDuck is an American company. We in DuckDB Labs are based in Amsterdam. MotherDuck are based in Seattle, and they are funded by venture capital, and they build all sorts of cool data warehouse and cloud features on top of DuckDB. So you can share your database, you can work on the same database concurrently, and they have something called hybrid or dual query execution, where part of your query runs in MotherDuck and other parts run in your local DuckDB instance, which is great for privacy preserving queries where some of the data just cannot leave your laptop. So to sum up, I can now give a more complete definition of DuckDB. DuckDB is an in-process analytical database system that has this state-of-the-art internal architecture and supports most of the cloud and file formats that are out there. Overall, I think the claim that big data is dead is quite true. It's not really a problem anymore to keep up with scaling data sizes. The performance of these systems are converging, and the key is now ergonomics and open file format. And strangely enough, persistence and mutability are hot topics. Thanks everyone for sticking around, and see you near the champagne.
Thank you, Gabor, for your presentation. And I guess it's question time. So maybe someone has. See one hand.
Thank you very much for starting this fantastic discussion about big data. Actually, I had a question exactly about this aspect. So how you were able to solve the problem of 5 V's, which is characteristic of big data, and at the same time, ACID principle of ACID transactions, which are included in DuckDB. Thank you.
Okay, so yes, it's tricky because it's easier to build an engine if the data is static, of course. What DuckDB does is that it takes a lot of the lessons from more obscure, less well-known academic systems. One of these is called Hyper, which was developed in the Technical University of Munich. And it actually turned into a spin-off company that was bought by Salesforce. And its internal architecture is explained in details in scientific papers. So there is an entire paper about the MVCC model of Hyper, which is the optimistic concurrency control that they employ so that they don't have to do locking, but you can do parallel access, concurrent access with transactions while guaranteeing snapshot isolation. So you have all these database technologies which allow you to be both concurrent and guarantee the correctness of the transactions.
Okay, one more question from Discord. Is there any way to define aggregate UDF in DuckDB?
Is there any way to define aggregate UDFs? The honest answer is that I don't know. I think there must be one, but also aggregates are more tricky. As a workaround, what could definitely work is to do an aggregate that puts everything in a list and then pass that list along to Python. Obviously, from a performance perspective, this may not be the best, but this works for sure.
Any more questions? Yes.
Thank you so much. Maybe like a practical question. So assume you have like 2 machines that run some process of DuckDB and you want to pass data from one machine to another machine. Would you have any recommendation about a file format? Obviously, writing a Parquet file would work, but any recommendations, even passing around the DuckDB file itself? What would you recommend?
Yeah, that's a great question. So the DuckDB file format evolved through the last couple of years, but in late 2023, early 2024, it reached a point where it's now backwards compatible. So you can just move around that one DuckDB file, and that will be other DuckDB clients of different versions and of different programming languages and different architectures will be able to read this. And it scales really well. So those TPCH experiments, those were usually run by DuckDB on a single file, which sometimes was around 20 terabytes. So it scales well, but DuckDB also has something called export database, which will just dump a bunch of Parquet files, and that also works if you want to transfer data.
Another from Discord. Do you still need PySpark nowadays? Iceberg plus Polars could work instead.
So the question is, do we need PySpark? We actually have in DuckDB an experimental API that replaces the PySpark API and then runs DuckDB inside. So if your workload happens to work with that, then you don't need PySpark anymore. Spark is a technology that you still need if you have tens of terabytes of data. So I do still benchmark work in the graph space, and we have these generators where you have to generate a complex graph of 30 terabytes. I wouldn't run it on DuckDB. That is still something that belongs to Spark.
And another from Discord. How long did the 100 terabyte benchmark take on laptop?
The 100 terabyte run on a server. And that took 1.5 days because there were a few bad apples. There were a few queries that really didn't want to bode well, and they took like 6 to 7 hours each. So that was 20 hours, and then the rest of the queries were basically 1 hour each. And on the laptop, that's faster. So that was significantly less than a day.
And another one, any suggestion for learning material for new SQL syntax that DuckDB introduced?
Right, so we have a page in our guides that's called Friendly SQL, and it has all these innovations and tasteful borrowing from other systems like pivoting, column star syntax, exclude, and so on.
And for now, I see that's the last one. How large the DuckDB community is versus other competitors?
So how large is the DuckDB community? Well, we do check the stars on GitHub. So we are around 30,000, ClickHouse is around 40,000, and Polars is also around 30,000. So we are all in the same ballpark, with ClickHouse having a significant head start because ClickHouse was already a pretty mature system around 2016. We have a Discord with more than 2,000 users, and we have a sizable GitHub community with many people reporting issues, contributing to the documentation, or just participating in discussions.